Hello, Professor. This is the video for my assignment 3. In part A, we are working with image convolution, one of the core operations behind how CNN actually processes images. The idea is simple. You take a small matrix called a kernel, slide it across the image, pixel by pixel, multiply the values element wise, write the result to an output array. That's the convolution operation. For question 1A, I created a kernel to detect 45-degree lines running in slash direction. The positive values run along the 45-degree diagonal and the negative values suppress everything else. When you apply it to the image, you can see the edges aligned at 45 degrees get highlighted in the output. For question 1B, I created a 135-degree kernel, lines going in the backlash direction. This time the diagonal goes the other way, so it picks up edges running top, left, bottom, right. For question 2, we applied three kernel as edge detection kernels. Kernel 1A, a corner sensitive kernel, it responds strongly to diagonal intensity changes, highlighting corners and diagonal edges. Kernel 2, the Laplacian kernel, it detects edges by measuring the second derivative of intensity. It responds to rapid changes in all four directions. And kernel 3, the full Laplacian, which includes diagonals. This one is more aggressive. It picks up edges in all eight directions and produces a sharper result. In part B, we are building and training a convolution neural network on the CIFAR10 dataset, a standard benchmark dataset. We normalized the pixel values to the 0, 1 range and 1 hot and encoded the labels before training. Now, starting with question 3, did the network uh, overfit? Yes, it did. Looking at the accuracy curve, training accuracy is the blue line, validation accuracy is the red dashed line. Around about 20 to 25, you can see the gap start to widen. Training accuracy keeps climbing while validation accuracy plateaus around 65 to 68%. That divergence is the classic sign of overfitting. The model is memorizing the training set rather than learning to generalize. Question 4, how many layers the model has? The answer is 5 layer. A conv 2D layer, max pooling 2D layer, a flattened layer, a dense layer, and a dense output layer. Question 5, purpose of each layer. The conv 2D layer slides 30 to filter across the image, each learning to detect a different feature, edges, texture, color, gradients. The max pooling layer downsamples by taking the maximum in each 2x2 window. This reduces computation and makes the feature roughly translation invariant. The flattened layer reshapes the 3D feature, maps into a 1D vector so they can flow into the dense layer. The first dense layer with 128 neuron learns high-level combinations of those features. The final dense layer with 10 neurons and softmax outputs a probability for each class. The highest one is the model prediction. For question 6, I added two more convolution layers to the model, going from 32 to 64 to 128 filters with an extra max pooling after the third conv block and a large dense layer of 256 neurons. Now, comparing the results between the two models, the deeper model learns richer, more hierarchical features, edges at the first layer, shapes at the second object, object parts at the third. As a result, validation accuracy typically improves by 3 to 6%. However, the deeper model is also more prone to outfitting because it has more parameters. The train well gap tends to be wider than in the original model, and each epoch takes longer to run. For question 8, I added dropout at 3 points in deeper models, 25% after the first pooling, 25% after the second, and 50% before the outlier. Question 9, asked to explain dropout in my own words. Dropout randomly switches off a percentage of neurons on each training step. So if you set dropout to zero point 0.5, half the neurons in that layer get zeroed out randomly for that batch. This helps because it stops neuron from relying too heavily on each other. Each neuron has to learn features that are useful on its own, not just in combination with specific neighbors. During interface interference, when you're actually making predictions, dropout is turned off and all neurons are active. Their outputs are scaled to account for the ones that were dropped during training. When you look at the accuracy curves with dropout, the gap between training and validation accuracy is noticeably smaller. The model is still learning, but it's overfitting less. This wraps up my assignment 3 in part A. We explored how convolution kernels work to detect lines and edges in images. In part B, we trained a CNN on CIFAR 10, analyzed overfitting, deepened the architect, and applied dropout to improve generalization. Thanks for watching.